All right, so we're going to talk a little bit about buffer data and specifically about how we buffer data and we move it into the GPU. Over the last coding exercises, you saw me try to put together something with OpenGL and a little window with a triangle. You noticed that we didn't actually send explicit lines or triangles or objects to the GPU. We actually created a buffer that then we put into a buffer object that was then attached to a vertex a VAO, an attribute object, which was then connected to it's a mess. And so we're going to talk a little bit about all those different pieces in this lecture. So let's get in there. So as we talked about in previous lectures, OpenGL is capable of drawing geometric primitives. It's able to do points, it can do lines, it can do triangles, it can even do quads and triangle strips and other types of more interesting things that are built on top of these ideas. But generally speaking, at the core of it, it's still just triangles and lines and points. So the way we need to define the geometry is we need to store it in a way that OpenGL understands. And so we know that 2 points in space is a position in space, right? X and Y. And with 3D data, we just add a Z. But the OpenGL doesn't really get the window coordinates until the last step of the rendering pipelines. So, the way, as we went through in the coding example, right, the output of the vertex shader stage is going to provide OpenGL with effectively a set of numbers in the -1 to 1 range. And later, this turns into Windows coordinates by way of a transformation from that. So when we created our triangle in that example, we were not manipulating that triangle. We weren't putting it in 3D space. We were only putting it in 2D space because it was then automatically passed on to the fragment or the pixel shader. And so as you can kind of see below here, we've got the first point, which is at 0, so that top point in the middle, because the most left and the most right are -1 and 1, not 0 to 1, as you might expect. And so 0 is actually in the middle of the screen. And then 0.5 is sort of halfway up from the center point, not all the way, and not halfway at the screen, but in the middle. So we can create a triangle that is sort of by using this and ensure that it's in the same place every single time. So as we mentioned in the previous lecture in the coding example, what is a GL float? Well, it's just a float. The thing is, the goal with OpenGL is to run on many different platforms. It's got to run on Windows, it's got to run on OS X, it's got to run on Linux, it's got to run on weird little Raspberry Pis and things. And so on every single platform, a float may be represented differently. What if your CPU only supports 16-bit floats? They do exist, right? So the code, the OpenGL code, wants to be portable, meaning it will run everywhere. Obviously, easier said than done. It doesn't actually happen in practice, but we do our best. And so GL float and like a GL everything is really meant to ensure the portability of the code. So let's define, how to represent, some geometry in 3D. And so we can have a triangle with a x, y, and z value. Call this P0, and x, y, and z1, or P1, and x, y, and z2, or P2, or 0 indexed. So we can have and define a triangle in that way. Now, as we showed when we were coding, we need to find a way to read them, and so we can't give. We can give the GPU these things, but it takes a long time, and so it's better to just create a long buffer and have somehow the GPU know that every every third number is a point, and that for every 3 points, that's a triangle. And so that's what we mean by buffering the data. We take the data and we kind of stuff it into a buffer, and we say, okay, X, Y, and Z, that's 1 point, and each one is a float. And so you can kind of see that to do this with C++ or to do with code, all you have to do is you take all those values that we had previously, and we stuff it into a vertex or a float array, where the first vertex the first point in this example would be at -1x, -1y, and 0z. In fact, all of these will be in 0z because right now it's flat. And then the next variable, so we can very quickly look at this and say, okay, these are 3 points, and what the values of those points are. So we might want to add other things into a vertex as well. In the future, we may want to pass in the color or the normals or the UV coordinates of a particular vertex. We also want to add maybe the what's called the binormal and tangent vectors, which actually we only need one of them. And if you can think of why, it's a good little thought exercise of why we only need, if you know what a tangent and a binormal is. Binormal is a normal, is orthonormal to the tangent and to the normal, so you can understand maybe why you only need 2 of them. But still, you might want to have a lot of data for each vertex, and so we can define the geometry kind of buffer, the vertex attribute designation, which we were doing before in the code example, and we can pass in, say, 3 3D positions, or this could actually represent 1 position and a normal and a color, and so on and so forth. So for the time being, we're only going to define the talk about positions, but as we were talking about in the coding example, it's really important to think about this piece, because at some point you're going to have to take that data and connect it to an actual vertex shader, and that shader needs to read in that data. And so your definition of what the vertex definition looks like, both on your CPU side and on your vertex shader program side, need to match, and that's being done by connecting the attribute as we were doing very briefly in the previous coding example. So we'll talk about that in this lecture as well. And so how do we know if we're sending 2D points or 3 2D points? Well, it really comes down to the definition, right? As we were talking about just a minute ago, how do we pass in how do we set the attribute for a particular vertex attribute? And in this case, we're saying, okay, it's a size of 3, it's a float, and it starts at 0. And so this line is very annoying, and so we can kind of try to say, like, the above line, it reads something like, the vertex that we will read starts at location 0 of your array and ends at location 3, and you'll read this as individual values of floats, and there's really no reason to normalize that information, and we're not skipping any spaces as in stride, and we're beginning at the beginning of the memory location. It's a lot of stuff to say, but it tells you a lot about how you would interleave other potential attributes and so on in the future. So at the end of the day, though, it's quite clear, right? This particular line of code is just really saying we're reading 3 things that are floats, and most of the other parameters we're not using yet, so you might not care about it. So yeah, this is what we're able to use to make kind of a buffer object, an object that's the buffer. Yeah, the names get really annoying, but you just kind of have to know VAO, VBO. There's also VIOs, which we'll get into later, but for the most part, VAO and VBO tends to really cover most of the bases. So, this is the code that we had previously in the previous coding example to define the geometry and then pass it into our GPU. So let's talk a little bit about what each one of these things is doing. So the first thing we do is we construct the VBO. We do that by first defining the data, which in this case we have 3 points. And then we go and we generate the VBO, which is going to contain our buffered data. And we then take that data by way of the GL buffer data call, and we pass to the GL array buffer this data. I mean, the GPU knows to copy in the amount, the size of, so it knows that memory size that then passes it in. And as I was mentioning last time, the GL static draw flag is used to tell the GPU a little bit about how we're going to use this data. So if we're going to change it all the time, if it's dynamic, then we might want to tell the GPU that. So we might want to put it in a different kind of memory location that perhaps is less optimal for reading, but is more optimal for writing, because we're going to change it all the time. Whereas a GL static thing might be a little bit faster to read, but much harder to write. And so, we want to give the GPU an opportunity to sort of do the best thing it can do, and OpenGL really simplifies this across many different pieces of hardware, so you never have to think about it. So kind of going back a little bit, this is the information buffer. This is actually the data that we're passing in, right? This is going to create an object on the GPU. This is going to then bind the GPU to that location, so it's telling the GPU, okay, we're going to operate on this particular buffer, so the next thing we do is going to be specific to that. And this is also going to say how we're going to use it and then we're going to also load that data into that. Next, we're going to use the buffer vertex object by connecting it to the shader program. So this will differ a little bit, but this name, the position buffer, is going to be the name of the input in the shader program, and then we're going to enable that ID. So notice, if you do this and that name doesn't exist, it's going to give you an error. It's going to freak out, or at least the position buffer ID will be 0, and then whatever you do next may crash. And so you do have to kind of pay attention to this stuff as you write it. So this enables it. And then below is what we were talking about before. It sort of tells the vertex shader how to read from that buffer we set in the VBO above. So let's go through it again. Right, this locates the position, the actual attribute in your shader program. This line will make that particular attribute active. If you don't do that, then it won't activate, and then you won't get anything funneling through there. So that's why. And then this defines to the shader how to actually consume that data. So the GL vertex attribute pointer function, again, you can really spend a lot of time here, and when you create really novel and more interesting vertex descriptions, like they're passing in colors, you're doing this and whatever, you start to use a lot of these pieces, but for the time being it's going to look pretty simple, right? Because you're going to say, okay, here are how many components, and here's how to read that buffer and how to parse through it. So yeah, it doesn't get too complicated quite yet. Great, so now OpenGL has our data, and we got to draw something. So how do we draw it? Well, we call this function GL draw arrays, and we tell it what type, the triangles, and we tell it how many triangles? No, that number is actually how many points that we have. So a triangle should have 3 points, and so this is a little bit of a gotcha with OpenGL. It's more about the vertices that you're passing in versus how many primitives you're actually rendering. And this really comes into play when you start to mix in things like the VIO, or the vertex index object, which is really, really useful. So again, to kind of go through it again, we are rendering in the triangle mode. We are starting from 0, and then we're passing it the number of vertices. So we can render other stuff as well. We can render multiple triangles, we can render multiple lines, but we can also do what's called a triangle fan, which is a little bit of a more efficient way to pass in many triangles that share a set of points. Similarly, We can also have line strips or line loops, which you may ask, why not just do a triangle at that point? That's a different subject. We also have the triangle strip, which is actually pretty useful. So if you can imagine a sphere is actually two triangle fans and then a number of strips around the middle, which is a very efficient way to draw something as complicated as a sphere. And why is it complicated? Well, try to programmatically define a sphere, and you'll find out quickly it's one of the harder primitives to draw. So this is just honestly the beginning. Even though this is the core of what OpenGL does, and for the most part, you don't really learn or have to know too much more about OpenGL than what we've already learned. We have to learn a little bit about how to render two specific targets and manipulate things and make more complicated vertices, and definitely we're going to learn a lot more about how to make shader programs that are more interesting and compelling and do more stuff. But for the most part, this is kind of it, right? We know how to take data and pass it into the GPU, and that's about it. But we haven't talked about lights, we haven't talked about transparency, and more importantly, semi-transparency and alpha blending, right? How do you draw things that are on top of each other that are also happen to be see-through to some degree? These are subjects that are not exactly the easiest thing to do. So keep in mind, while we've sort of covered the blunt of OpenGL and how to do stuff with it, this is just the beginning of what we're going to start doing with it. So the VAO is kind of a confusing name, I agree. It's not an array of vertex objects. It's a vertex array object. So it's an object containing vertex arrays, yes, but it contains the VBO, so it actually contains the data, and it also contains the state machine. And this is important. If you load up a different VAO to a different, the vertex, connection from that VAO to the shader may differ. And so you have to kind of keep this in mind. When you change the VAO, you're changing a lot more than just the object that you're rendering. More often, you actually manipulate the VBO, not the VAO. You kind of leave it alone, unless you really want to be fancy. So yeah, if you're interested about the state machine of OpenGL, I recommend you check out these links, in particular the OpenGL context, which really open.gl is a great resource, and I think can really kind of explain to you, if you're ever interested, some of the stuff that we've been going through and how to manipulate this particular one. We'll talk about SFML, SDL, right, just that. So yeah, the state machine is something that you'll start to really get used to into thinking about, because once you set a particular setting, it will stay that way. So you're always kind of fighting the state machine to make sure that you're in the right setting before you start doing anything. And most bugs in OpenGL will be related to that. So sometimes instead of really fighting the state machine, you can use VAOs instead to configure different arrangements of settings and flags for different stages of your programs or for specific objects and so on. So you can get quite efficient there. But yeah, that's a little bit about how we got memory into the GPU. And next we're going to start to kind of dig into some code. Great. Bye.